Support for this grassroots community television program comes from U.S. Trust. From wealth structuring to investment management, U.S. Trust's global perspective, unique team approach, fiduciary platform, and more than 200 years of experience provide for the kind of insights, solutions, and expertise that have a worth all their own.
So welcome. My name is Howard Haber. I'm a general member and a former trustee of the Aspen Center for Physics. Welcome to the Maggie and Nick DeWolf Winter Lecture Series. Maggie and the Nick DeWolf Foundation have supported public lectures here for 28 winters, and the Wheeler Opera House graciously provides this beautiful historic space. Their generosity and the generosity of every lecturer makes it possible to share with you the new research that is moving the frontiers of science forward. It's our way of thanking the Aspen community for supporting the center for 51 years. Each year, for 6 or 7 weeks during January, February, and March, groups of 60 to 100 physicists spend an intensive week here sharing their latest research with their colleagues in formal meetings and also informally on the lifts, on the cross-country skiing trails, or on snowshoes. I am here this week participating in the High-Energy Physics Conference, whose title is Higgs Quo Vadis. And that title was chosen before we knew that there was going to be a new pope announced today. So there you go. And I can tell you from my experiences here in Aspen, both at winter conferences, this is my 5th, and the summer workshops that we hold here for 15 to 16 weeks from the beginning of June till the beginning of September. I've been coming here almost every year since 1989. Aspen is just an amazing place to do physics, work hard, and enjoy the beautiful surroundings. And when we leave here, we are refreshed with new ideas. Aspen is a great place for inspiration, both winter and summer. Now, this is the last of the winter lecture series, but every summer we also have summer programs going on here, and we have a summer series, so if any of you are back here during the summer, please look out for the ads in the local newspapers and come to the lectures. Also, if you want to know about other upcoming events, please sign up to be on our email list. The sign-up sheet is in the lobby, or go to our website, www.aspenphys.org. So tonight, we're very fortunate to have Matt Strassler as our speaker. Matt got his PhD from Stanford University in 1993. In fact, I knew Matt when he was a graduate student at Stanford because my institution at UC Santa Cruz is a mere 50 miles to the south, and I spent many days at Stanford. And I can tell you, even though Matt was a young guy and he was supposed to be learning from me, I can tell you that over the years I've learned much more from him than he did from me. He is now a full professor at Rutgers University in New Jersey, an expert on particle physics, string theory, and a frequent consultant to the experimental physicists working at the Large Hadron Collider, which is the place where the Higgs boson was discovered last summer. I just want to mention one other thing. Matt is very interested in promulgating science to the public, and he runs a website called Of Particular Significance, and in your program you can find the URL to that website. The aim is to bring the excitement of particle physics and other areas of science to a wider audience. So without further ado, I present you Professor Matt Strassler.
I'm sorry, very kind. All right, well, how's the sound? I guess it's all right, yes. Well, it's a great pleasure to be here in this beautiful theater in this beautiful town. I've sat where you're sitting and watched operas here, so it's fun to have the opportunity to talk to you about one of the really exciting things to happen in science in the past year, the most exciting thing to happen in quite a while in particle physics. We are indeed in the middle of a conference and where new information, new data is being presented to us on a daily basis. Some of the people who participated very actively in the discovery of this particle, and even some who were interviewed in the New York Times just last week, in the articles that you may have seen, are here at this conference. And so it's a very active, exciting moment for us. On the screen there, you see a picture, with an aerial photograph, which shows Geneva, Switzerland, over here. This is the Geneva airport. And underground, underneath this circle, is the world's largest particle accelerator, the Large Hadron Collider. And it is inside this accelerator that Higgs particles were made and discovered over the past couple of years. Now, many of you are aware that it was July 4th of this past year that white smoke started coming out of the chimney at the CERN laboratory, and the director general came out onto the porch there and said, we have a Higgs. Well, actually, that's not quite what he said. We have something that looks a lot like a Higgs. But I think by now the data is such that we're pretty much convinced that indeed or at least a Higgs boson has been discovered. And the purpose of this talk is to answer the two questions: what is it, and why should you care? All right, well, if you go to the newspapers and you ask this question, you usually get an answer which looks something like this. Well, okay, first of all, God particle, all right? Physicists do not use that term. God particle doesn't come from religion, and it doesn't come from science. This term comes from advertising. Somebody was trying to make money, so they invented this term, and the media loves it, so that's why it's floating around. But this is not the biggest problem with the statement. The biggest problem with the statement is that it's wrong in a big way. There's two statements that are true that I'm going to make now, and these are the ones I'm going to try to explain to you in today's talk. The first is, it's not the particle that gives mass to things, it's the Higgs field. You don't hear people talking about the God field, even though that's the thing which really matters. This is the thing that provides mass, but it doesn't provide mass for everything. It just provides mass for some really crucial things, the known elementary particles, and if it didn't do this, we wouldn't be here. The other statement that is true is, well, we do care about the Higgs particle. Boson, by the way, is just a type of particle. It's not a big deal as a name. The Higgs particle, what is it? Well, it's a little ripple, a little wave in the Higgs field. And the reason we care about it is by discovering the Higgs particle, we confirm that the Higgs field actually exists. And that's what we actually care about. So those are the two statements that are going to be what I'll be trying to explain in today's talk. Okay, well, if we're going to talk about the Higgs, we need to talk about mass. What is mass? Well, you all sort of know what mass is. You want to get through a door and there's someone in your way. That someone is a little child. No problem. You just scoot them out of the way. If instead the person who's in your way is a football player, you will have more difficulty. Okay? The football player has more mass. It is harder for you to move the football player than the child. Here's another example. You take a box, you put feathers in it. Let's put the box on some ice, make the ice nice and wet so there's no friction, all very simple. And you give the box a push, and it'll fly across the ice pretty quickly. On the other hand, if you take the same box, and you fill it with bricks, so it's got a lot of mass, and you give it the same shove, it's not going to end up going so quickly. One more example for fun. You're standing there and someone tosses a pillow at the back of your head. Okay, this is not a big deal. The pillow doesn't have a lot of mass. It just bounces off the back of your head. Your head doesn't really, this doesn't really bother your head. But if someone, on the other hand, were to toss a rock at your head, well, you should duck. Okay, your head is going to have a lot more trouble stopping the rock. Okay, that's mass. Matter. Matter is ordinary stuff, ordinary material. We're made from matter. The Earth is made from matter. Everything around us is made from matter. Ordinary material is what I'm referring to here. And ordinary material has mass. well, okay, so what are we? What is material actually made from? And where do we get our mass from? Those are questions I'm going to try to answer before we get going into the question of what the Higgs is all about. So let's consider what we are actually made of. Let's start with a prime specimen of our species and ask, what is he made from? Well, let's go down by a factor of 100,000. We'll take a microscope and we'll look at things 100,000 times shorter in distance, and there we will find the biological cells that make up our bodies. And if we go down another factor of 100,000, we will find atoms. This is actually a sort of picture of atoms, a real picture. It's made with a microscope that sort of acts like Braille. It actually feels where the atoms are. So this is the closest thing to a picture of atoms that you can get. Now, what are atoms made of? Well, you can't really make a picture of an atom, so this is kind of a cartoon. Atoms have electrons on the outside, those little blue things. They're so tiny that we don't even know how big they are. They're too small for us to measure. So I draw them as dots, but they're much smaller than I've drawn them. And in the center of the atom is an atomic nucleus. And that's also really tiny, but we do know how big that is. It's another 100,000 times smaller. Right? The nucleus is made of neutrons and protons. I've drawn them in different colors. And they're about the same size as the nucleus itself. And if we go inside a proton, this is what we would see. Lots and lots and lots of little particles running around in there. Now, some of those particles are quarks. Some of you may have learned that a proton is made from 3 quarks. Well, that's kind of true. It's made from 3 quarks, and then a bunch of little particles called gluons, and then additional quarks and antiquarks. And they're all running around in there really fast, banging into each other and banging into sort of the edges of the proton. It's a pretty complicated thing, the proton. And the neutron is pretty much the same. OK, so just summarizing all of that in one slide. The things I want to point out are, I mentioned electrons are too small for us to know how big they are. We haven't ever been able to measure their size. The same is true of quarks and gluons. And so those particles, which I've just circled, are, as far as we know, elementary particles. By elementary, I mean they're not made from other things, as far as we know. They're indivisible, as far as we know. Protons and neutrons, on the other hand, are not indivisible. I showed you that they're made of other stuff. But the interesting thing is that that's actually where most of our mass comes from. Most of the mass in an atom is in the nucleus of an atom. So most of our mass is in protons and neutrons inside of a nucleus. And protons and neutrons are not elementary particles, and they don't get their mass from the Higgs field. So most of your mass, most of the mass of everything around you, doesn't come from the Higgs field at all. So what's the big deal? Well, the big deal is that even though electrons have a small fraction, less than 1% of an atom's mass, that mass is really important. And here's why. The point is that, the point is that if you were somehow to be able to make the electrons in this room have a smaller mass, all of the atoms in this room would grow. In fact, if someone could flip a switch and turn off the masses of the electrons, make all the electrons massless, we would just explode. Okay? No electron mass. If the electron mass goes to 0, atoms get infinitely big. They just fall apart. Now, the Higgs field is what gives the electron its mass. So if there were no Higgs field, or if there were a Higgs field but it were off instead of on, in a sense that I'll explain, then the electron wouldn't have a mass. There'd be no atoms, and we wouldn't be here, nor would the Earth or anything like it. Okay, so this is actually a big deal. The electron mass is critically important for atoms, and therefore the Higgs field, which provides that mass, is also critically important. So my experimental friends, I am a theoretical physicist, I consult for my experimental friends, but they're the ones actually finding this thing. They're out there trying to find the Higgs particle, not because the Higgs particle by itself is so important, but because we really want to understand this thing called the Higgs field. And the Higgs particle is our way of doing that, for reasons I will explain. This whole story about looking for the Higgs particle is part of a quest that goes back over 100 years. It was just at the turn of the last century that the electron was discovered. That was the first elementary particle. It has a mass. The photon was discovered a little while later. It doesn't have a mass. So right off the bat, you have this question, well, why do some particles have mass and some particles not? There are four forces of nature that we understand quite well. I'll come back to them in a minute. One of them is gravity, and one of them is electricity, or more precisely, electric forces and magnetic forces. You come across those in daily life. There are two other forces which we don't come across in daily life. One is the strong nuclear force, which is what holds those protons and neutrons together. And then there's the weak nuclear force, which is responsible for radioactivity. It's what helps the sun shine. And it's a very important force as well. It was discovered in the 30s and studied in the 40s and 50s and so on. And a very interesting thing happened at the end of the 50s, where it was realized that there were certain properties of the weak nuclear force that you could see experimentally, and they were completely incompatible with the electron having a mass, which you could also see experimentally. These things were just inconsistent. It was a paradox. Higgs and others introduced the idea that a field, which we now call the Higgs field, changes the environment in which everything moves, changes the whole universe, in such a way that it resolves this paradox and allows the weak nuclear force to do its thing and the electron to have its mass. And is this idea correct? Well, the idea made a prediction. If the idea was true, then little ripples in this field, Higgs particles, should exist. They should be discoverable. And that is what, in fact, has been achieved in the past year. Now, I should mention, Higgs and friends had this very simple idea, but there were many variations of this idea that were possible, and they were invented over the following decades. And so there's still this question, which of these variations on this idea is the correct one? So the basic idea of what is happening at the Large Hadron Collider in Geneva is, first of all, to confirm the Higgs field exists, the idea is make Higgs particles. That's been achieved. But then we want to understand the Higgs field, or fields, because there might be more than one, and that means we want to study the Higgs particle, or particles, in great detail. And so that's what's the next phase of the Large Hadron Collider's operations. Okay, so I told you that the electron gets its mass from the Higgs field, and the proton and neutron don't get their mass from there. Well, where do they get their mass from? This is a bit of an aside, but it's still a nice one, and it gives us a chance to talk about a very important concept in physics, which is energy. Now, you all have some sense intuitively for what energy is. If you're not feeling very energetic, you're kind of lethargic, you're sitting on the couch watching TV, you're not moving very much. Okay? No energy there. Now, on the other hand, if you're feeling really energetic, you're running out there to get to the gondola, go up on the slope, ski downhill, you got lots of energy. Okay? Moving things have energy just because they're moving. And that type of energy we call, well, I'm going to call motion energy. The jargon term for it is kinetic energy, but let's just call it motion energy. It's the energy due to the fact that things are moving. That's a pretty obvious and intuitive type of energy. But as Einstein and others at that time, back at the turn of the century, realized, even something that is standing still, even something that's stationary, has energy just because it has mass. And how much energy does it have? Well, that's the one equation that everybody knows. The amount of energy it has is E equal to the mass m times the speed of light c squared. And since the speed of light is fast, this is a big number. Okay, if I could turn all the mass in this little ball into energy, I could blow up the entire Aspen Valley. Fortunately, I can't do that, nor can any of the pyromaniacs in the audience. Now, I do have to nip a potential confusion in the bud, because it's widespread. Many people learn in school or read in books, and there's a good reason for this, that the equation E equals mc squared is always true. No matter what the ball is doing, E is equal to mc squared. This is not the interpretation which particle physicists and most physicists in the field give today. And that'll be important, so that's why I have to take a moment for it. The interpretation to E equals mc squared that we give is that when an object is stationary, its energy is equal to mc squared. When it's moving, it has not only mass energy, but also motion energy, so it has more energy, and therefore E is greater than mc squared for something that's moving. Okay? That'll be important to keep in mind. Okay, so where does the proton's mass come from? Well, there's all these things running around inside it. They've got lots of motion energy. Okay, on the other hand, if you have a proton just sitting there in front of you, it's not moving, it's not going anywhere. The things inside it are going around in there, so they have lots of motion energy. So this object has lots of energy, but it's not moving. So it doesn't have any motion energy, yet it has energy. What must that energy be? Mass energy. The mass energy of a proton is due to all of the things inside running around. There's actually a little bit more energy in there just holding those things inside. And there's a little bit of mass energy for a proton that comes from the fact that the quarks have masses, so they have mass energy. But those masses are pretty small. It's not a big effect. Now, where does all this motion energy come from? Well, it comes from the strong nuclear force, which holds the proton together and keeps these things moving. So that's where most of the mass in a proton, and therefore most of the mass in your body, actually comes from. It's the strong nuclear force, not the Higgs field. Okay, so we've answered the two questions. What are we made from? Electrons, protons, and neutrons. The protons and neutrons are made from quarks and gluons. Where do we get our mass from? Mainly from the strong nuclear force, but a crucial minority of our mass comes from electrons, and those masses are essential for the existence of atoms, and those masses wouldn't be there if the Higgs field weren't on. Again, I'll explain what I mean by that. Okay, so back to this statement, the Higgs field provides masses for the known elementary particles. Well, what are the known elementary particles anyway? I've given you a few of them. Here's a list. First, there are some particles which colloquially we tend to call the particles associated with forces. For every type of force, there's a corresponding particle, or particles. The gravitational force, gravity, is associated with a particle called the graviton. We've never actually discovered the graviton, but we're quite confident that it exists. It's very hard to make one. One type of particle we certainly know exists, and you know this because I can point at the screen with a laser, is a photon. The photon is the particle which is a particle of light. And light is associated with electrical forces. The strong nuclear force is associated with those particles called gluons that I mentioned. And the weak nuclear force is associated with particles called the W's and the Z, which differ from the others I've just mentioned because they have a mass, while all of the others don't. Then there's the particles which we often call matter particles. Those include the particles that make us up. There are three types of neutrinos. There is the electron and its heavier cousins, the muons and the tau. There are 6 types of quarks. Most of the ones that make us up are up and down quarks, but there's 4 other types of quarks which are heavier. And finally, we have a new one, the Higgs, or a Higgs, to add to the list. And it's kind of a force particle in some ways, and in some ways you could argue it was a bit of a matter particle, so okay, we haven't decided where to put it. It's kind of a new thing. That's part of what's so exciting about it. Now, of course, for the Higgs particle, there's a Higgs field. I told you that the Higgs particle is a ripple in a Higgs field. Well, that's true for all of these particles. For every particle, there's a corresponding field. Or maybe I should say it the other way around. For every field, there's a particle. And you'll see why I put it in those terms in a couple of minutes. Now, before I do that, let me just remind you one last time. All of the particles on this page, except the Higgs itself, interestingly, if I turned the Higgs field off, all those particles would be massless. And that would be bad, because there'd be no atoms. Okay. I've been talking about elementary particles, and you may ask, what the heck is an elementary particle? Well, that's going to be key to understanding what the Higgs field is actually doing. So let's spend some time on that. I've been drawing them as dots. Well, okay, they're not dots. In fact, it's impossible to come up with any one picture which really captures the full richness of what elementary particles can do. They're really quite amazing things. But I'm going to take now a picture, I'm going to sort of produce a picture for you which is a little closer, or at least captures something else that really, it captures more of what particles can do, what elementary particles can do, and what they are. So I'm going to describe them here as little ripples, disturbances in an elementary field. And we have a name for these little ripples. We call these things quanta. Quanta is the plural of the word quantum, and that quantum word is the same word that appears in that scary thing called quantum mechanics, which is actually the way our world works. It works according to rules of quantum mechanics. And so the word quantum, well, you may as well find out where it comes from. Right? So we're going to learn that today. Okay? So elementary particles, we're going to find out they're little ripples, little waves in elementary fields. We've got to learn a little bit about waves. We've got to learn about fields. And we have to learn what quanta are. And that's going to be the next significant chunk of the talk. Okay? All right, so a little interlude. One of the simplest little systems that you study in physics class is something that bounces. Okay? This is a heavy thing on a spring. Okay, this is bouncing or vibrating or oscillating. Those words I'll use interchangeably in this talk. Okay? And there's some interesting things that you can notice very quickly about something that's bouncing on a spring. First of all, there are two very interesting things to ask about a bouncing thing. How often is it bouncing? How many times per second does it bounce? That's called its frequency. Okay? And then there's the question, how high is it bouncing? And that sometimes is called its amplitude. I'll just call it its height. Okay, let's call the frequency F and the height or amplitude A. And there's a couple of things that if you play with one of these for a few minutes, and you all should, I mean, just buy one at the store and just watch what happens. There's a couple of interesting things to notice. First of all, you can make the amplitude, the height of bounce, whatever you like. So for example, I can make the bounce really small, or I can make the bounce really big. It's entirely up to me. But the really interesting thing is no matter how big I make the bounce, the frequency is the same. Okay, here's a big bounce. Watch as the bounce gets smaller due to friction. It's bouncing with the same frequency. Now this is actually really important for musical instruments, for those of you who are musicians. This is why, as a musical instrument like a guitar string gets quieter, the pitch, the tone remains the same, because it's bouncing the same frequency, even though the bounce is getting smaller. Okay, so the amplitude can be whatever you like, but the frequency is always the same. F is always the same, unless I change something. For example, okay, here's the frequency if I just leave the spring alone. But what happens if I tighten up the spring? For example, supposing I wrap the spring around my hand. So now it's tighter. Let's see what happens. Oh, it bounces faster now. Right? If I loosen the spring, it bounces more slowly. Okay? So if I tighten the spring, I get a faster bounce, I get a higher frequency. If I loosen the spring, I get a slower bounce, I get a lower frequency. Now, what is true for a spring is also true for waves. How many people here own a Slinky or have a Slinky at home? Oh, you all should have a Slinky. Everybody should have a Slinky. You can learn so much physics from a Slinky. It's fantastic. Okay, you can make waves on a Slinky. You can make waves of all sorts of different types. You can make waves that go back and forth. You can make waves that go up and down in nice ways, like, let's see if I can get this right. Here we go. Oh, this is fun. Okay, you can make all sorts of great stuff. Now, you can see this wave is clearly an oscillation. It's a vibration. It's a bounce. It has a frequency, and it has a height. I can make the height whatever I want. I can make the height bigger, hopefully without breaking it. If I wait a little while here, it'll just through friction, or maybe I'll just tap a little bit, see if I can get it down. I can make a wave with small height. But you notice no matter how big the height is, the frequency is the same. So what is true for the spring is true for the Slinky. It's true for waves. And it's also true that if I sort of tightened up the Slinky, I would get faster waves. Well, okay, it's a little harder. There we go. Okay, the waves are faster now. Okay, so what is true for the spring is true for the Slinky. It's true for waves in general. Okay? This is all going to be important. Trust me. Okay. Now, remember where we were. We were trying to learn about waves because we wanted to know what elementary particles are. And I told you that elementary particles were little wave-like things in elementary fields, so we needed to know what waves are, but now we need to know what fields are. Okay. Well, what are elementary fields? Well, what are fields? You kind of have an intuitive sense for what a field is. You go drive around here, and maybe somewhere near Aspen, you can find a farmer's field. Okay, it's a big open expanse. Maybe there's nothing in it. Or maybe it's got wheat growing high, or corn, and maybe the corn's just standing there, or maybe it's sort of, swaying back and forth. Well, this is your intuitive notion of a field. The notion that physicists use is not wildly different. The word field was used because there were some similarities to the things that we work with. So let's start with the wind. The wind is a nice field. All right, what do we mean by the wind field? You know what I mean by the wind. What is a wind field? Well, let's measure the wind over here. Okay, supposing I know the wind over here. I'll measure the wind over here. I'll try to measure the wind over here. Okay, all of you could help me out. We could measure the wind everywhere in this room. If we knew what the wind was at every point in this room, we would know what the wind field was. The wind field is simply the information about what the wind is everywhere. Okay, so the wind field, in some sense, is something that is everywhere. And what the wind field is at a point is just what the wind is. I mean, this is not a big deal. Right? Now, what can the wind do? That's the interesting part. Now, the wind in this room, when I look around here, everyone's hair looks pretty good. Well, almost everybody. And that tells me that the wind is, it's off in the following sense. The average value of the wind in this room is 0. The wind is calm. But if we opened up the back room and opened up the doors there and opened up the front doors and the windows and turned on big fans, we could get the wind blowing here and our hair would be blowing around. And then we would have a steady breeze, and in that sense, the wind field would be on. Its average value would not be 0. It would be, 10, 20 miles an hour pointing towards the stage, let's say. Okay, so a field, the wind field can be on or off on average. It can be dead calm or it can be a steady breeze. If it's on, then it has some strength. Okay, so that's another thing to know about the wind field. Here's another one. The wind field can have waves, and you know this because you can hear me. What are waves in the wind? Well, I'm speaking, and as I speak, I'm making vibrations in the air, and as the air moves back and forth, that means if you were to measure the wind right here, it would be this way and this way and this way, back and forth. And the waves in the wind are propagating out towards your ears, and when they get to your ears, the wind is going back and forth like this, and it's making your eardrums flap, and your brain is then interpreting that flapping as sound. Okay? So, those are 3 things about the wind thought of as a field. The field is everywhere, it can be on or off, on average, and it can have waves in it. And those waves have interesting physical interpretation. These facts about the wind are facts about fields in general. Fields are things which exist everywhere. They can be on or off in the sense that on average they can be 0, or on average they can be non-zero, and they can have waves. But there's one more thing. We live in a quantum world, a world described by quantum mechanics. And a field can do one more thing. It has one more property we need to know, which is that the waves of this field are actually made from particles, which is a pretty weird idea. But it's true. And I'm going to try to explain to you now how that works. Before I do that, though, let's talk about one more example, the electric field. Now, the electric field, what's the electric field? Well, how many of you have been on top of a mountain in Aspen during a thunderstorm? Not 0. Has your hair ever stood on end? How about, you take off your hat after you've been skiing and your hair is sticking up? Well, this is because there's an electric field nearby. The electric field is making your hair stand up. The electric field is something you can measure everywhere, and so it is indeed something that exists everywhere. And it can be off on average, and again, everyone's hair looks okay, so my conclusion is that it's off in this room, but if we had a strong electric field, everyone's hair would be standing on end. We'd certainly know it. Okay? And if you're at the top of a mountain, you may have, in a thunderstorm, you may experience this effect. Okay? So the electric field can be on or off on average. And the electric field has waves in it, and you know about this because you can see me, right? Waves in the electric field are what we call light. Now, in fact, it's not just light, or it's what physicists call light. When physicists talk about light, they don't just mean the light that you can see. They mean everything from radio waves to microwaves to X-rays. They're all different types of waves in the electric field, just with higher or lower frequency. All of these waves are made from particles called photons. Now, what the heck are these things? Well, let's come back to this slide. This was the slide that said, if you have vibrations, a spring or a slinky, or waves in general, they have a frequency, which is determined by the properties of the slinky or the properties of the spring, and they have an amplitude, which you can choose. And we went through all these things, and the problem is that in a quantum world, one of these statements is false. Anybody know which one? The physicists do. Anybody else? The statement that is false in a quantum world is this one. You cannot make the amplitude of oscillation, the vibrational size, the size of the wave, the height of a wave, as small as you want. How many of you have a dimmer switch at home? You've got a light bulb and you can turn it down. Okay. MP3 player or stereo, probably everybody's got one of those. You turn the volume down. Well, you would think, quite naturally, that you could turn that dimmer switch down and then turn it down again, and then turn it down again, and then turn it down again, and turn it down again. You could do this forever, ad infinitum, ad nauseum, right? You could get the light to be dimmer and dimmer. You could get the sound to be quieter and quieter and quieter and quieter and quieter. Right? On forever. At least if you had perfect technology, okay. Granted, no real dimmer switch can actually do that, but you can imagine that would be possible. But in fact, it's impossible in principle in this world that we live in. It's not true. If you were to turn down the volume or turn down the brightness, you would discover that gradually, as you turn it down, it starts going down in jumps. And eventually, you turn it down, you turn it down, you turn it down, you turn it down, and then you try to turn it down a little bit more just to try to get half as much brightness, and instead you get nothing. This is true. Okay? I can't show this to you with any any ordinary light bulb in the room, but you can do this with experiments in scientific laboratories. Okay? There is a wave of smallest height, a quietest possible sound, the dimmest possible flash in our world. And that dimmest possible flash is called a quantum. All right? And in particular, what we call that quantum, if we're talking about light, is we call it a photon. That's a particle. You notice it's a little wave, but it's a wave whose height is the smallest allowable. That's what a photon is. Now, why is this thing a particle? What's particle-like about it? Well, one thing that's particle-like about it is you can't break it up into pieces. You can't take it and divide it up into 3 parts and then get a third of a quantum over here, a third of that. It doesn't work that way. The thing holds together. You can emit one or absorb one, but you have to do a whole one, not half of one. The thing will travel around as a unit. It'll bounce off walls. You can have 2 of them, you can have 3 of them, you can have 4 of them. You can't have 7.286 of them. This is what we expect from particles, from, let's say, pebbles or baseballs. These are the properties that things we think of as particles have. And yet, this thing is still a wave. Another thing this object has is a mass. At least it can have a mass. Photons don't. But electrons are like this too. In fact, all the particles of nature are a quantum. Every particle of nature is a quantum of a wave in a field. So an electron is a quantum of a wave in the electron field. And the Higgs is a quantum of a wave in the Higgs field, and so on. It's true of all of the elementary particles. They're all waves of smallest possible height in that field. Okay? And some of them have mass, and some of them don't. Okay? This is real. You know, this is what's in your body. It's not some abstract thing. Okay? This is what you're made of. So think about it. It's pretty cool. Now, oops, let's go in the right direction. Okay, so we've learned the answer to the question, what are elementary particles? Every elementary particle is a quantum, that is to say a wave of smallest possible height in a corresponding field. And I'm going to keep drawing it like that. So, now, the really interesting question we can now start to answer, which is the one we all came to learn about. Where does a particle get its mass from? Where does the electron get its mass from? Well, a particle is a quantum. A quantum vibrates. It's a wave. It's a vibrating thing. Okay, well, you kind of know. If you have a vibrating thing in front of you, that thing has energy. You can't have vibration without energy. I mean, vibration is, there's energy in there. How much? Well, if you have a thing that's vibrating with frequency, f, and it's a quantum, that is to say it's the wave of smallest possible height, the energy which is required to make that quantum, or equivalently the energy that's stored in it, is given to us by the only other formula you really ought to know, aside from E equals mc squared. This is the other one. The energy stored in a vibrating thing, if it's a single quantum, is Planck's constant, h. This is a constant which describes how quantum the world is or isn't. And it was discovered around the turn of the century, of the previous century, by Max Planck. And you take Planck's constant and you multiply it by the frequency and you get the energy stored in the vibration. E equals hf. Couldn't be more simple. Remarkably simple formula. Okay, so you've got this vibrating object. How much energy does it have? It's just Planck's constant times f. But that quantum is just sitting there. It's not moving. This quantum I've drawn up there, it's not moving to the right. It's not moving to the left. It's just sitting there. So how are we going to interpret that energy when we look at that quantum? It's a stationary object. It has energy. We're going to say, just like we did for the proton, oh, this thing has mass energy. And we know what the formula is for that. Einstein said for any stationary object, the mass energy is mc squared. Well, these things must be the same. And in fact, it's true. The frequency of vibration in this quantum is what we interpret as mc squared. And the mass energy of an elementary particle is nothing other than its vibrational energy, which you wouldn't know if you drew it as a dot, but it's a little wave, and it's vibrating in there. And the energy in that vibration is mc squared. It's the mass energy. Okay. Pretty cool. That's what electrons are, okay? They're little vibrating things. And now we have the question, wait a second, this whole talk was supposed to be about the Higgs field. So where does the Higgs field come into this story? Well, let's turn it on. Let's imagine this is a quantum that already has a bit of a mass. Let's turn on the Higgs field. What will the Higgs field do to this field that has a quantum in it? So the Higgs field is what we're going to turn on. This is some other field that has a quantum in it. So let's keep them separate. This is one field. Let's say maybe it's the electron field that has an electron sitting in it. And then we're going to turn on the Higgs field. Remember what I told you the Higgs field does. When we turn it on, just like any field, it means it develops a non-zero average value. When it's off, it's just 0 on average. When it's on, it's not 0 on average. Now, what is this field doing? Well, it's changing the environment in which everything moves around. And it has the following very interesting property. It tightens, it's like tightening up a spring. It makes the electron field and other fields springier. Okay, so what does that mean? Well, we learned what happens when we take a spring and we tighten it up. Okay, you take a spring and you tighten it up, and its frequency gets larger. It starts to bounce faster. So you turn on the Higgs field. Here it is in blue. The world is changing, and the frequency of this little quantum is growing, and therefore the energy in this quantum is growing. And so what the Higgs field has done is it's made the frequency larger, so it's made the energy larger, but that means it's made the mass energy larger because the vibration energy and the mass energy are the same thing. And so therefore it's made the mass larger. That's how the Higgs field makes masses bigger. You make the Higgs field larger, the masses get larger because the Higgs field is tightening up the springiness of the electron field and the other fields in nature. Okay? So now we know. This is how the Higgs field provides its mass for the known elementary particles. If you make the Higgs field larger, what you're doing is making the electron field stiffer, like a tightened spring. And that means the electron field's oscillation frequency gets bigger, which means that for a single stationary quantum, remember a quantum is just the wave of smallest height, that's what we call an electron. The electron will have larger energy when it's just sitting still, and that means its mass is bigger, because the only energy it has when it's sitting still is its mass energy. And that's the story. That's how the Higgs field works. And this works for all of the known elementary particles except the Higgs field itself, which is a little more complicated, Higgs particle itself, excuse me. And again, if the Higgs field were off, all these particles would have no mass at all. Okay, well, I've answered the key question that I set out to answer, but I've left out something. You know, these particles don't all have the same mass. The top quark, for instance, has a mass that's hundreds of thousands of times larger than the mass of the electron. Same is true of the Higgs and of the W and Z particles themselves. They're all very, very heavy, very, very massive compared to the electron. And the electron is millions of times heavier than neutrinos. Well, gosh, that's odd. Why is that? All I've told you so far is that if the Higgs field is off, all these particles are massless. And I've told you that if the Higgs field is on, they get a mass. But I haven't told you why they get the masses that they do, why some of them have very large masses and why some of them have very small masses. So you could rightly ask, why are the masses so different? Another question you might ask is, well, where does the Higgs particle's mass come from? And you could ask, yes, you've told me that the Higgs field is on. Fine, but why is it on? And why does it take the value that it has? Why isn't it much bigger? And therefore, why isn't the electron and all the other particles' masses, why aren't they all much bigger than they are, or much smaller? I haven't answered those questions. Here's a couple more. How do you know there's only one Higgs field? Maybe there's more than one. How do you know the Higgs field isn't some very complicated thing made out of other fields in some complicated way? The answer to all of these questions is, I don't know. I haven't the faintest idea. Well, more precisely, there are lots and lots of speculations. I can tell you my theory colleagues, some of whom are here, have made many, many, many speculations about this, but we really have no idea. The only way to answer these questions definitively is with experiments, and we have to find the right experiments to answer these questions, and any given experiment may not turn out to be the right one. We have very good reason to think the Large Hadron Collider will answer the two questions on the right. We expect that over the next decade, we'll be able to determine whether there are any other Higgs fields and any other Higgs particles, and we'll be able to determine whether the Higgs field is really an elementary field or whether it's somehow a more complicated thing. Whether we will get insights into the other questions is not clear. Maybe it'll be a decade, maybe it'll be a century, maybe it'll be more. We don't know how far we are from answering these questions. They are deep, profound, and open at the moment. So there's so much we don't know. How are we going to learn something? So this gets us back to the question, how do we use the Higgs particle to learn about the Higgs field? Well, how do we learn about other sorts of materials, or substances? What's a good way to learn about substances? Well, there's a classic strategy. It's not the only strategy, but it works very well in many cases, which is if you want to understand something, whack it. Make it wiggle, you know? Make a ripple and make a wave in it. It works. It's a really good idea. For example, one way to learn about the air is to study sound. You can learn a lot about air from sound. You study the speed of sound. You study how easy it is to make sound. You study how the sound changes with temperature and pressure. These are all things you can study, and you learn something about the air. Another nice example is the Earth. How do we learn about the Earth? How do we know about anything about the inside of the Earth? Seismologists study the Earth by looking at the waves that come out of earthquakes, that move through the Earth, move through its various sections. It's a really good way, the only way really, to learn about the deep interior of our planet. Close your eyes. What musical instrument is over there? Well, if somebody plucks the instrument, you'll be able to hear, that's a guitar. And you can learn all sorts of things about the guitar from the sound. Another example, which I'll dig out of here. Here's a bell. It's a metal bell. You don't know anything about this bell. It's a blue thing. But you're going to learn something about this bell right now. Okay? You just learned a lot. Okay, you don't necessarily know what you learned, but you learned a lot. We're going to think about what you learned. We're going to do the same thing with the Higgs field. We want to learn about the Higgs field. We're going to whack it. We're going to try to make it wiggle. That means we're going to try to make waves in it. And we know what those waves are made from. They're made from quanta. And quanta are just Higgs particles. And so we're going to make Higgs particles and we're going to study them. And that is going to teach us something about what the Higgs field is. That is the strategy. OK. So remember, the reason we went through all this trouble to build a big machine to try to find the Higgs particle was because we wanted to understand the Higgs field. Because the Higgs field is necessary, the Higgs field being on, in particular, is necessary for our very existence. It's a mysterious thing. We really want to understand it. OK. So now, what's the Higgs particle? Well, we already went through this discussion we know that every elementary particle in nature is a quantum of a wave in a corresponding field. So that's true of the Higgs particle. Remember, I told you at the beginning of the talk, the Higgs particle is a little ripple. Well, now you know, it's not just a little ripple, it's the littlest ripple in the Higgs field. It's the smallest, it's the wave of smallest height that you can make. Okay? Here's one right there. Okay? Here's the blue thing showing that the Higgs field is filling the universe and it's changed the environment. And here is a little ripple in it where the Higgs field is a little bit bigger and a little smaller, and that thing can move around, and that's a particle. Okay. Now, how do we make Higgs particles and how do we learn something about them? Well, we're going to use this metal bell to learn something about as an analogy. Okay, so step A, we strike the metal and make it vibrate. Step B, as the metal vibrates, it makes waves in the air. Those are sound. And step C, those sound waves, we need to detect them somehow. We'll use your ears. Your ears are excellent airwave detectors, right? Okay, here we go. Okay, now what do you notice? There are three very interesting things that you notice that we can ask about. One is, we can ask, what is the pitch, or the note, or the tone, or the frequency, right? The frequency of the waves in this bell determine the sound you hear, the note you hear in your ear. So that's one question we can ask. The second question is, given how hard I hit it, how loud was the sound that came out? How difficult was it to make this thing ring? And the third question we can answer is, how long did it take for the sound to die away? Three very obvious, simple questions, and if we answer those, we can actually learn something about the material and the shape of this bell. It would take a little work, but we could do it. Now, we're going to do the same thing for the Higgs field. Step A, we're going to try to make the Higgs field vibrate, and we're going to do that by slamming protons together in the Large Hadron Collider. We're not smashing particles together to find out what's inside them. We're smashing them together to try to get the Higgs field to do something. This is not easy. You're trying to make Higgs waves? Well, I'll tell you something. 1 in 5 billion proton-proton collisions is able to make the Higgs field vibrate just the tiniest little bit, make one quantum. It's that hard to make a Higgs particle. That's why we need such a big, powerful machine. You make the Higgs particle, it almost immediately falls apart into other particles. Those particles go rushing out. If we don't detect them, we don't learn anything, so we need to detect them using big machines called particle detectors, and I'll show you how big these are in a moment. Now, what are we going to learn? Well, for every question we've asked about the bell, there's a corresponding question for the Higgs. First question is, what is the Higgs particle's mass? Well, you already learned from a transparency just a little while ago that a particle's mass is related to the frequency with which it's vibrating. So asking the question how the bell is vibrating is equivalent to asking the question how is the Higgs field vibrating, but the Higgs field's vibrations, the Higgs field's frequency is just proportional to the particle's mass. So asking the particle's mass really is the same as question number 1 about the bell. Question number 2, how often do we actually make Higgs particles, is the question about how easy is it to make them. And that's equivalent to the question of how loud is the sound you get if you whack the bell with a certain strength. And the third question is, how does the Higgs particle fall apart? How long does it take? Well, those are questions that are related to how does the tone of this bell die away? And just as we can learn about the bell by answering those questions, we can learn about the properties of the Higgs field by studying these properties of the Higgs particle. So now we bring on the Large Hadron Collider. Now we know where we want it. Okay, so step A, we need to slam protons together. Okay, everyone ready? We're going to slam some protons together. Everybody watching? Here we go. Whoops. All right, I'll try that again. Sorry, I don't think this is aligned very well. Let me adjust things here. Okay, everyone concentrate for me, please. Okay, here we go. Now, this time for sure. Oh, that was worse than the last two. Okay, this isn't working very well. We need another idea. Okay, how about this? Oh, there we go. Okay, you do not aim one proton at one proton. You will miss. Okay, the trick is you get 100 billion protons going this way. You get 100 billion protons going that way. When the two clumps pass through each other, there's a pretty good chance the two of them are going to hit. That's how it's done. And then if you're lucky enough that you made a Higgs particle, or indeed anything else interesting, stuff comes flying out from the collision, and now you need to detect it. And so you use these big machines. They go by the names of CMS and Atlas. CMS is pretty big. By the way, these pictures are cutaway drawings. These are shaped more like beer cans. This is a cutaway drawing showing the complexity of CMS, and look at the size of the people. Okay, this is the size of a moderate-sized office building. Here's Atlas. Look at the people down there. Okay, it's even bigger. These are enormous devices that are used to measure these incredibly tiny particles to incredible accuracy. You should definitely have a talk about these experiments and how they work. They are amazing. All right, so CMS and Atlas are designed to detect the outgoing particles. And they're huge, and CMS is CMS may look smaller than Atlas, but it's so heavy you wouldn't believe it. Just amazing. Okay, so here are, again, just to summarize, our 3 steps. We need to make the protons slam together. Occasionally we make a Higgs particle. Then the Higgs particle falls apart into other particles, and we have to detect those particles in these 2 giant machines, Atlas and CMS. So how do you actually find the Higgs particle? How do you do that? Well, here's how it works. Okay? First, we smash protons together, and if we're lucky, we make a Higgs. Okay? Now, just imagine for the moment the Higgs is stationary. It needn't be. We can correct for that, but let's imagine it's stationary. How much energy does it have? Well, you know that. It's got the mass of the Higgs particle times c squared. Only problem is we don't know what the mass of the Higgs particle is yet. So we know it's got whenever we make one, it's got the same energy. We just don't know how much. But we do know that sometimes Higgs particles fall apart into particles of light, 2 particles of light that go off, flying out with no mass energy. Photons are massless, but with lots of motion energy. How much motion energy do the two photons have? Well, the total energy of those 2 photons must be the same as the energy we started with, because in particle physics, the energy you start with is the energy you finish with. Energy is conserved, as particle physicists say. So you started with a Higgs that had a certain amount of mass energy. We don't know what that energy was, but we do see 2 photons come out. So if we can measure those 2 photons and measure their energies, we'll know how much energy the Higgs particle had, and therefore we'll know how much mass it had. The only complication is that when 2 protons collide and 2 particles of light come flying out, it doesn't tell you there was a Higgs made. It might have been made for some other reason. So this is what people actually do. This is real data. This is part of the discovery data from July. You make a plot, and what you plot is the number of proton-proton collisions that make 2 of these particles of light, 2 photons. You take all of them. And then you make a plot. How many do I have versus the total energy that those 2 photons carried, which I have to measure very carefully. And when you make this plot, you see that there's lots and lots of processes that give you photons of all sorts of different energies. Those are sort of randomly distributed. But then there's a few extras right here. And those extras are not random. They all have pretty much the same energy. And those are coming from those rare times that you make a Higgs particle, that's 1 in 5 billion collisions, and 1 in 1,000 times it falls apart into 2 photons, and you detect it, and you measure the total energy you find. They all end up right about here, and you find the same thing in Atlas as in CMS. Now, this data was also supplemented by data from Higgs particles that decayed in other ways, and the data has gotten stronger and stronger and stronger over the last 6 months. We are all convinced now there's a particle there, and almost certainly a Higgs particle. That's how it was done. Okay, we found the Higgs particle. What do we do? Well, I already mentioned those 3 questions that are good to answer. There's a couple of others that are important and related to questions that I put on earlier slides. First of all, are there other types of Higgs particles? Maybe there's a second, maybe there's a third, maybe there are 5. We need to know. And the other question that's natural is, well, maybe the Higgs particle gets made or falls apart in ways we didn't expect. And those are all things we're going to try to understand over the next decade at the Large Hadron Collider. But as I emphasize, that's not the end, because there's still all those other questions about why do the different particles have the different masses that they do, and why is the Higgs field on in the first place? Those questions are still out there. So this is just the end of the beginning. So let me bring this to a close. I've told you that elementary particles like electrons and photons are just quanta, that is to say waves of smallest possible height in the elementary fields that we find everywhere in the universe. The Higgs field is very special because it's on. On average, it's not 0. And because it's not 0, because of the way it interacts with other fields, it makes those fields stiffer. It makes it harder for them to vibrate. So when they do vibrate, they vibrate faster. There's more energy in those vibrations for each quantum. And that means, when we translate that, that's the statement that there's more mass for a particle. And if the Higgs field were turned off, this wouldn't be true. The electron, being one of these, wouldn't have a mass, and there'd be no atoms. A lot of other things would go wrong too, but that's already pretty bad. There'd be no ordinary matter. The Higgs particle, just happens to be a boson, is a quantum of the Higgs field itself. It's a little ripple in the Higgs field, the littlest possible ripple. Its existence confirms there really is a Higgs field in nature, that I'm not just fooling you with ideas. And as we study this particle in detail, its properties will tell us more about the Higgs field as we get a lot more data and a lot more studies from the Large Hadron Collider over the next decade. The discovery of the Higgs boson represents the end of a quest that goes back to the 1960s, which is when Higgs and friends actually discovered this. And I should mention it wasn't just Higgs. Higgs is the lucky guy who got his name on it, but there were some other people too. Brout and Engler are names you should know, and also Hagen, Guralnik, and Kibble. And those 6 people all wrote papers that were in one way or another related to this idea. There were some people before them who contributed important ideas, some people after, but those are the ones who we will all remember. This is all part, however, of a century-long ongoing saga to understand the particles of nature and their masses. And many puzzles are still open. So for the young people in the audience, don't worry, this isn't going to be done by the time you get through college or get your PhDs. This is going to be going on for a long time. So my talk has come to an end. The quest to find the Higgs particle, at least the first one, has come to an end. But the quest to really understand what's going on with the Higgs field, to understand the elementary particles of nature, well, that is going on. That will be going on for quite some time. Thank you.
Thank you very much, Matt. I'll open the floor to questions.
Mass and gravity seem to be totally linked and intertwined, but does understanding the Higgs field have implications for understanding gravity?
A classic question, beautiful question, very often asked. The thing is that gravity had to do with mass back in the days of Newton. And when Einstein came along, he said, no, that's not quite how it works. Actually, gravity has to do with energy and momentum. Now, you know energy and mass are related. For slow-moving objects, for a stationary object, energy and mass are proportional. For a slow-moving object, energy is almost the same as the mass. And that's why Newton gives such accurate answers. But in Einstein's theory, gravity is really about energy. That's why, for example, 2 photons can attract each other gravitationally, even though they have no mass at all. So no, it's just appearances. Actually, the Higgs and gravity are completely unrelated, because the Higgs really has to do with mass, and gravity really has to do with energy. And the relation between those is more complicated than just simply that they're the same.
So if you have a light-emitting diode, converts, as I understand it, I'm probably wrong, but converts electrons to photons, or there's an interaction that creates photons from electrons, would that remove the mass from an electron?
So the question is, how do light-emitting diodes work? I mean, you're not really asking the right guy. But basically, more generally, there's a process which can occur outside of a material. I mean, light-emitting diodes are materials, right? So there's material science in there you have to know. But if I take an electron and I take an antiparticle of an electron, that's called the positron, and I bring them together, they can transform into 2 particles of light. Now, what happens there is not so different from what happened with the Higgs particle. I started with a particle that had mass energy, and I turned that mass energy into motion energy of the photons. The same thing happens if I have an electron and a positron. They have mass energy. They might have some motion energy too, but when they turn into 2 photons, it's a conversion in which energy is conserved. Whatever energy went in is the same as the energy went out. But mass is not conserved. The mass you start with is not necessarily the mass you end with. Okay? So indeed, with the Higgs particle, I start with a big, heavy thing. Well, not big, a small, heavy thing, and it turns to photons that don't have any mass at all. The energy that I started with is the same as the energy I ended up with. But the mass I started with is completely different from the mass I ended up with. Similar kinds of questions in the context of material science, but it's trickier. So that's why I avoided your question a little bit. I can try to answer that question in more detail, but privately.
Let's go here.
Is the particle harmonic in nature, and is that quantifiable?
Is the particle harmonic? What do you mean by that?
Repeat the
Yeah,
question.
but I haven't understood the question yet.
I'm looking at it more, I'm not a physicist, I'm a musician. So
Yeah.
I'm looking at it in terms of harmonics.
Ah.
The way it vibrates is the vibration, is the energy within it. Is it an energy that is a vibration more or less within its spectral way?
Can I try to, I mean, I think, you know, I play music too, so I have some sense of what you might want to ask. I mean, certainly it is true that what we're looking at here, the fact that, you know, the electron has a mass, is a way of saying that is that the electron field has a preferred frequency. Now, that's true of a guitar string, it's true of a violin string, right? There's also true of any object that can vibrate. It has certain resonant frequencies. And the masses of particles are, in some sense, the resonant frequencies of the universe. Now, one nice thing about a musical instrument is that it has a harmonic series, that if I pluck a string right in the middle, I can actually get a tone that's 1 octave higher and has double the frequency. We don't have any examples of such simple relationships in particle physics. It doesn't seem that the particles of nature have any sort of harmonic relations of that type. It could have happened, but it doesn't seem to be the case. So the mystery of where the particle masses come from does not seem to have any simple answer in terms of simple mathematical relationships. It's much more complicated, and that's why we're having so much trouble figuring it out.
I have a couple of questions about the experimental results from CERN. When they announced last July the Higgs Boson finding, there was a certain significance level that they were talking about. I think it was called sigma.
Right. It is in some sense.
With the new data, has that value increased?
So the question is when the data came in from, when the data was announced in July, people said, well, we see this particle with a statistical significance of some number of, sometimes people say sigmas, or the more statistically precise term is standard deviations. What does this mean? Well, this is the statement that if you want to know whether you have a perfect coin, and it has 50% heads and has 50% tails, if you only flip it 4 times, you're not necessarily going to figure that out. Right? You have to do something many, many times before you're sure that your coin is fair. Or if you roll a die many times, you may not get 1, 2, 3, 4, 5, and 6 with equal numbers unless you do it many, many times. You have to do something many times before you're confident in what you're observing. There's a similar sort of thing when we're discovering a bump on a plot, like the ones I showed here. So those bumps, they could just be accidents. They could just be that, well, you know, look at the data. The data is the black dots. The data is bouncing all over the place. That bump could just be by accident. Well, how confident are you that that bump is real and not by accident? The way you describe how confident you are is you say, well, it's a certain number of standard deviations away from random. 3 standard deviations is moderately convincing. 5 standard deviations historically has proven to be really convincing in the sense that a lot of 3 standard deviations excitement goes away after more data is collected. But once something gets to 5 standard deviations, it's very, very rare that it disappears, unless somebody made a mistake. Okay, but we have some of the best experimentalists in the world doing this stuff. They didn't make mistakes here. Right? So those are real data. Now, you ask, has the significance gone up? Absolutely it has. As more data is collected, that bump has become sharper and sharper. I didn't happen to put pictures of what those bumps look like now, but the data that we're seeing at this conference, every time we see more data, it gets more significant. So yes, we're more and more and more confident that thing is really there. We'll come back to you, I think, if you don't mind.
Now it's 10 sigma.
10 sigma on the total?
10 sigma total.
Okay,
combined.
so when you combined all the data together from any one experiment, from either CMS or from Atlas, but you took all of the different measurements they made, it was about 5 sigma in July, and now it's about 10 sigma. So much that you stop counting sigmas. I mean, what's the point? You're confident. It's there. It doesn't matter. I mean, you know, how confident are you that I'm here? Okay, 7 million sigma or 9 billion sigma? Do we care? No.
Let's go over right there.
Can the Large Hadron Collider measure the speed of the photons that are emitted? And if so, is that related to the strength of the field, of the Higgs field?
No, the speed of the photons is set simply by the fact that the photons are, well, there's actually, sorry, I didn't repeat the question, did I? Yeah, so the question is, can the Large Hadron Collider measure the speed of the photons? That's, let's say, question 1. And question 2 is the speed related to the Higgs field in any way? So let's start with question 1. Actually, the answer to question 1 is sort of yes, to a certain precision. It's critical for these experiments that they have precision timing at about 1/billionth of a second. So they can measure how long it takes for the photons to get from where they're produced to a distance of about a meter where they're actually measured. But we know how fast photons go because they all go with the same speed. They all go with the speed of light, at least if they're in empty space. And the speed of light is not affected by the Higgs field. One of the really fascinating things about the Higgs field, unlike a lot of other fields which you could try to turn on, is the Higgs field leaves the properties of space and time basically the same when you turn it on. It changes the environment, certainly, and it changes the masses of certain particles, but it leaves Einstein's relativity, which determines for you that the speed of light should be a constant, it leaves it completely unaltered. That's a very special feature.
That kind of dovetails into my question. GR taught us that there is a relationship.
GR being general relativity.
Mass, energy, and space-time.
Yeah.
And something about mass tells space how to curve, and space-time tells mass how to move.
Right.
We've talked in your presentation a great deal about mass, but you haven't mentioned space-time. Does GR come into play at all in the Higgs?
Does general relativity have anything to do with the Higgs? That's really related to the question I answered earlier. So as you said, there's a way of saying this, that mass tells space-time how to curve, and space-time tells mass how to move. Well, the more precise way to say that is energy and momentum tells space-time how to curve, and space-time tells energy and momentum how to move. That's really what general relativity says. Now, it is true that if you have an object like a planet or an apple falling from a tree, its energy is just mc squared plus a tiny little bit for motion. So that's why the statement that mass tells objects tells space-time how to curve is basically right, as long as you're dealing with an object that's not moving very fast. But really, it's about energy and momentum. And that insight of Einstein's really moves mass, the question of where mass has come from, to a different place. And that's why, in fact, general relativity and the Higgs, and the properties of the Higgs are really disconnected. And you see that in the mathematics. We don't have to combine them at all. They're really fully separate. But it really has to do with Einstein's insight about energy and momentum.
Might mention the gravitational force being incredibly small
Well, there's,
on the scale.
it is, Howie reminds me to mention that it is also true that we don't have to account for gravity for another reason, which is it's so amazingly weak. So in our experiments studying the Higgs particle, the gravity of the Higgs particle plays no role. And the experiments are really fast, and the gravitational pull of the Earth is unimportant. So there's another sense in which we don't need to worry about it, which is basically gravity has almost no effect in any of our particle physics experiments. And we kind of wish it did, because then we could study it. It's actually really hard to, one of the reasons we haven't discovered the graviton, and won't anytime in the near future, is it's really hard to make these things. You know, gravity is so weak. Think about it. You can lift your arm using electric forces against the gravitational pull of the entire Earth, and you don't even think about it. Gravity is amazingly weak. It's very hard to study.
Does Higgs particle have a spin?
The Higgs particle, does it have a spin? What does it mean to have a spin? That's a tough question for a general audience. You know, I have enough trouble explaining spin to graduate students. There are a couple of ways to talk about spin, but I don't have a very intuitive one. There is a sense in which an electron is like a little spinning top, but not really. Okay? There's a sense in which it's spinning, and so you can say, well, it's spinning, you know, sort of oriented this way, or it's spinning oriented that way. The electric field has a direction. The electric field can point this way, or it can point that way, or it can point this way. The Higgs field does not point anywhere. In that sense, it is spin zero. There is no preferred direction picked out by the Higgs field. That's part of why it doesn't change the properties of space and time. If I turned on the electric field in this room, it would make this direction in space very different from that direction. But when I turn on the Higgs field, all the directions remain much the same as they did before. That's part of what makes the Higgs field so special. It's the only example in nature of an elementary field of that type, if it's elementary, which we don't yet know for sure. I think we're going to have to also keep track of time because we're going to be out of here. But.
Any other accelerator be able to have enough energy to show the existence of the Higgs particle? The boson, or is a large hadron the only one that is coming?
Well, the first Higgs particle was probably created by human beings in 1989. And it was made at the Tevatron Collider near Chicago. The problem is making one is not enough. Or you see in this data, you've got to make a lot of these particles to see them peak up above all the other processes which can occur. And remember, I mentioned only 1 in 1,000 Higgs particles decays to 2 photons. So you've got to make enormous numbers of these things. So unfortunately, although the Tevatron made thousands, tens of thousands of these perhaps, it only got just a hint. And if it had run a little longer, or if it started a little earlier, been just a little more efficient, or if the Large Hadron Collider had been delayed a little longer, the discovery might have occurred there, or at least evidence. But they were just a little late. And so that's why the discovery happened in Europe, not in the United States.
Is the Higgs field ever off?
The Higgs field is never off. It would take an enormous amount of energy to turn the Higgs field off, even in a small region. And so once the Higgs field is on, for reasons we don't know, I should remind you, we don't know why the Higgs field turned on, but we know, partly because the Higgs particle is so heavy, has such a large mass, that to get the Higgs field to shift, remember what the Higgs particle is. It's a little wave. It's a little shift, local shift in the Higgs field. It takes an enormous amount of energy to make one of these things. So to get the Higgs field to turn all the way off would take a vast amount of energy, even in a small space. So we can't do that. It's certainly not going to happen spontaneously. Oh, very, 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 very early in the universe, maybe it was off for a little bit. But we can't actually prove that. But I mean, we're talking about extraordinarily short times, and there's some speculation which goes into how that happened. So we don't really know. But it hasn't been off for a very long time.
Does the Higgs particle deteriorate into elementary particles other than photons?
Yes. Now, does the Higgs particle deteriorate, is the word you used, into other particles? Deteriorate it's sort of a, particle decay. It's worth mentioning. Particle decay is not about things that aren't elementary falling apart into things that are. Particle decay is really a transformation. And an elementary particle of one type can transform into elementary particles of different types if they have a smaller mass. So, for example, the particle called the muon, which is one of the heavier cousins of the electron, falls apart into an electron, a neutrino, and an antineutrino. But the muon is most certainly just as elementary as the electron is. So the Higgs particle may be elementary. It can fall apart into elementary particles, like photons. It can fall apart into quite a few other particles, and that's in fact really exciting because we have lots of things to measure. It can fall apart into bottom quarks. It can fall apart into particles called taus, into muons. It can fall apart into let's say two electrons and two anti-electrons, or two muons and two anti-muons. It can fall apart in a bunch of things, and our friends here are busy measuring those. How often do these different things happen? And by measuring how often these different things happen, they get some insight into how the Higgs field works. So these are very important measurements indeed.
So it's really a transformation.
It's really a transformation, not a falling apart. And that story is a little long, so I won't tell it here. But that's how particles work, yeah.
Okay, so we have 3 more questions, so we'll do the 3 hands I've just seen. So let's start here.
In your bio, it says that you would like to see high-energy physics become a spectator sport, or a sport something?
High-energy physics is a spectator sport. You're here.
That's true.
It is a very good spectator
in
sport.
your dream society, your dream reality, how would we react to all these pieces of news and so forth? How would it become a sport?
In our dream society, how would particle physics specifically, and maybe science in general, become more of a sport? Well, I mean, in some sense, the tools are already there. It's just, there are wonderful magazines. There have been for many years, like Science News comes out once a week. You can be a spectator to that. There are now, of course, lots of blogs and lots of videos online at YouTube. It's really not the problem that the information isn't there. The problem is how to excite people and bring them to places where they can find it. Now, a lot of that, of course, starts in school. And it also starts with the parents of the kids who are in school. One of the reasons I give lectures like this, some of you may have young kids or grandkids, and some of you are young. And, you have opportunities to point people to things that may excite them about their world. So that's one aspect of it. The other is, to try to get people to think a little bit more about the world they live in and take it less for granted is something which always requires a certain level of encouragement. But again, I think we can do a lot of that with the young. And getting them, to play with slinkies and springs and so forth is part of that. To look at the world around you, look at what it does. You can learn a great deal about it with fairly simple questions. And so I think in an ideal society, we would have better educated science teachers in grade schools and in high schools who themselves had more contact with what the forefront of these scientific fields are actually doing. And that we would have more opportunities to also bring science to the public through the news media with journalists who actually get the science right, as opposed to saying, well, the Higgs particle, the Higgs particle gives all the mass in the universe, and just getting things completely wrong. There's problems like this that we would have to address.
Do you envision a day when Las Vegas bookmakers might lay odds on different experiments?
Will the Las Vegas bookmakers lay odds? Right now, I'd just be happy if there was white smoke coming out of the chimney at CERN.
So there was a question, yeah.
My question isn't exactly what you're talking about, but it started with what your lecture started about. Is there more than one of these elaborate accelerators? I mean, it seems like such a giant mission of its own.
We have come to the point that there is only one accelerator of this type. The entire world scientific community, those people who work in particle physics from all sorts of different countries, came together to make this machine happen. There was an American machine that was planned, that was being built in the 1990s and then was canceled. That was called the Superconducting Super Collider. Not the best of names, but it would have been a great machine. We would have made these discoveries earlier. But the challenge of doing these types of experiments has increased over time. And so the difficulty of building multiple accelerators of this type in different parts of the world has become more difficult. However, I should emphasize that there are different types of accelerators. For example, this is an accelerator that smashes protons together. You can also imagine accelerators that smash electrons into anti-electrons, or positrons. And those machines are very different in their properties, and they allow you to study other things. So there will probably be only one machine like the Large Hadron Collider, but there may be other types of machines, and indeed there are other types of machines at lower energies doing other things, studying other things today, and there will be in the future.
Okay, so any more? Okay. Did you?
Oh, sorry, I'm a little hoarse. You had mentioned earlier in your lecture that all matter is made of waves. I was wondering why you can walk through some waves and not others. And ones like sound, you can walk through.
Right.
The ones you can walk through, is there anything you can do to them so you couldn't walk through them?
Well, why can you walk through air and sound waves in air? And why can't you walk through a tree and the little ripples in the tree? Well, that has to do with two things. One is when you come into physical contact with material, what's really going on is a complicated interaction among the electrons in your body and the electrons in the object that you're trying to walk through. Beautiful. That's probably the call saying, get off the stage. Okay, so first of all, there's that contact effect where your electrons come into contact, which are on the outsides of your atoms, are coming into contact with the electrons that are at the surface of that other object. Now, when you come in contact with the air is a gas. That means the atoms of the air are sort of independent of each other. They can move independent of each other. So as you walk, those atoms just get out of your way. Whereas in a tree or a piece of steel, the atoms are all linked together. And so it's not easy for you to push them out of the way. So it really has to do with the internal structure of the material that you're trying to push out of the way. Or that I should say, the electrons in your body are trying to push on the electrons in that material, and they either succeed, if it's air, in pushing aside, or not, if it's a solid.
So the waves of electrons in solids you can't get through, and the waves in sound waves you can walk through.
Well, but the waves in sound, the waves in the sound are waves in the air itself. So it's really not that you're getting through the sound waves; you're just getting through the air.
Or light.
Yeah, I mean you're okay. So Your question is actually a little bit tricky to answer without pulling different parts of the question apart. I think I need to think about how to answer it because of the way you've phrased it. So now we've lost the fellow who's supposed to close the session. So I will close it. Well, thank you all very much.
Support for this grassroots community television program comes from U.S. Trust. From wealth structuring to investment management, U.S. Trust's global perspective, unique team approach, fiduciary platform, and more than 200 years of experience provide for the kind of insights, solutions, and expertise that have a worth all their own.